Hi everyone. Okay, I'm going to try and pick up where we left off in class, which was in the middle of 8.1, Introduction to Magnetism. Just went over all the properties of magnets. You can have a look at that in my lecture notes. And I had started to introduce two different types of magnets. So the first type is here. It's an electromagnet. In 1820, Oersted found that passing a current through a wire deflected a nearby compass. And if you can imagine having compasses all laid out around a wire, if there's no current in the wire, those compasses would orient north as usual. However, when that current is turned on, the compass is aligned with the magnetic field produced by the wire. So this means that moving charges, specifically current in a wire, will produce a magnetic field. And these are two examples here, one where the current goes up and we have a magnetic field curling around the wire this way, and here the current is down and then the magnetic field is curling back into the page. So generally this looks like a coil of wire instead, and a common example is this solenoid. So a solenoid would be many coils of wire, here tightly coiled. This is supposed to be the wire. And then the magnetic field within the coil of the wire is roughly uniform. So we've seen uniform electric fields with parallel plates. The closest to that really is a solenoid for a magnetic field. It is not uniform outside of the coils of the wire. So you can see better images of that in my lecture slides if you look there as well. Okay, so the other second type of magnets is on this side. It's a permanent magnet. So permanent magnets are fundamentally linked to electromagnets because they're based on this principle that electrons have spin. So electrons within an atom will spin around their axis, and that essentially creates a moving charge. So that moving charge produces a tiny magnetic moment or a small magnetic field here. And so this is two orientations for that electron spin up or spin down, producing magnetic fields in two different directions. So what happens in non-magnetic materials is that all of those spins are just randomly aligned. In wood, for example, they're all randomly aligned and they cancel out and there's no magnetic moment. However, if we have a permanent magnet, that means that generally the spins are aligned, creating an overall magnetic field. So in ferromagnetic materials, drawn here, there are domains, usually about the size of 0.1 millimeters, but they can be smaller. And so these would be the domains, and within that domain, all of the spins align. So they're roughly all directed in the same orientation, and that creates a net magnetic moment in each domain. So in ferromagnetic materials like iron, those domains originally would be randomly aligned as well, still creating no magnetic moment. So that's why an iron nail on its own wouldn't produce a magnetic field. However, this is very susceptible to external magnetic fields. So if you were then to bring an external magnet towards this piece of iron or piece of ferromagnetic material, those domains would then align with the external magnetic field, creating a net magnetic moment and a net magnetic force between the materials. So that's why some of our materials are attracted to magnets and others are not. Also, ferromagnetic materials like this can retain the magnetization if you were to then remove the external magnetic field. Generally, they can stay magnetized. Sometimes heating or physical motion can help with retaining that magnetic field, and it depends on the material how well they can retain that. Okay. Let me know if you have any questions, and I'll move on to 8.2.